Today you're going to find the probability using a geometric or a binomial model. So when we determine if we have primarily a binomial model, we do this thing called Bernoulli trials. And essentially, we're going to follow bins. Okay, so B, which would mean binary, meaning you have to have two outcomes. Okay, the I, you have to have independence. Now that could be the 10% rule, which we will talk about here in a second, or it could be like a coin flip. Okay, the N, which applies to a binomial model, meaning you have a fixed number of trials. And the S would be the probability of success is constant, meaning it's not going to change. Okay? Now, the N is for binomial model. If we are just doing a geometric model, it's like biz. So if we look at our sample example, it says, suppose a cereal manufacturer puts pictures of famous athletes and cards in hopes of increasing the sales. The announcer announces that 20% of the boxes contain a picture of Tiger Woods, 30% a picture of David Beckham, and the rest a picture of Serena Williams. You're a big Tiger Woods fan, and so while you don't care about the other cards, you want to get that photo of Tiger. So how many boxes do you expect to open before finding him? Well, remember, this is a previous example we looked at earlier in the year. The act of opening a box is what we call a trial. And note, for each of our trials, notice we have only two possible outcomes, success and failure, right? We either get the Woods picture or we don't. The probability of success is the same for every trial. And if we know 20% of the boxes contain Tiger Woods, and therefore 20% of the boxes should be Tiger Woods. And as we open boxes, each trial is independent, which we talked about with our bins. And these three conditions technically make up the Bernoulli trials. Okay? So notice we're going to let X be our random variable, the number of boxes, until we have a Tiger Woods card. And we're going to build a probability model. So obviously, if we open the first box, we know that answer is 0.2. Okay? If we don't get a Tiger Woods card until the second box, which means the first box we open is a failure, and the second box we open is success. Notice if it's the third box, then that means the first two are failures, or 0.8 to the second power times 0.2. If we want the fourth one, notice we're going to have 0.8 for the first box, 0.8 for the second box, 0.8 for the third box, and then 0.2 for the fourth, because that's our success. Or we're having 0.8 to the third times 0.2. Okay? And this leads us to conclude this is our geometric model. Our failure, which is Q, to the x minus 1 power times P. So the question becomes, how many boxes might we expect to have to open? Well, since the probability of getting a tiger picture is 20%, or 1 in 5, we could expect to find his picture on average in the fifth box. Right? If I take 1 over 0.2, we do get about 5 boxes. Or the mean of a geometric model is 1 over the probability of success. So when we find out how long it takes to achieve a first success in a series of Bernoulli trials using a geometric probability model, it is denoted as geom P. The geometric probability model, notice we have P as probability of success, X is the number of trials until the first success, and we have that formula we looked at earlier. To find the mean, we'll do 1 over the probability of success and the standard deviation, the square root of failure, over success squared. Let's talk about independence. It is often a reasonable assumption, meaning especially for flipping a coin or rolling a die, etc. But remember, if we look at issues or situations where we are choosing our samples without replacement, it can become an issue. What you will see, especially when we talk about proportions in the upcoming weeks, we have this thing called the 10% condition. We know that Bernoulli trials have to be independent. If that assumption is violated, it is okay to proceed as long as your sample is less than 10% of the population. So here's an example for us to illustrate this. So we have Postoni. It is a global company specializing in communication security. They monitor over 1 billion internet messages per day and recently reported that 91% of emails are spam. Totally believe that one. Assuming that your email is typical and that you aren't using any spam filters, if your inbox collects mail overnight, about how many spam emails should you expect to have to go through to find a real message? Okay, so we know that our probability we're going to have spam is 91%. So therefore, we're going to have a real message. We're going to take 1 minus 0.91 to get 0.09. Okay, so this is our probability. It's a real email. Okay, so if I want to find the mean, we know this is geometric because we have 2 outcomes, right? It's either it's spam or it's not. We have the probability of success is constant. So if we have over 1 billion internet messages in a day, our sample was going to be less than 10% of the population. That's just a given. And then our 2 outcomes. Oh wait, we already said that. We have probability of success is constant, 91%. Okay, so now we can go back to our expected value. Okay, so in our expected value, remember we'll do 1 over the probability of success. So in this case, we'll do 1 over 0.09 and type that into a calculator. And it is about 11.1 repeating. And then just like with anything, we're going to write a statement in context. Okay, so here's our statement in context. On average, we expect to check about 11.1 repeating emails until we find a real message. So if we look at the next question, it says, determine what is the probability that the 5th message in your box is the first one that isn't spam. Okay, so we'll do this 2 different ways. We'll do it the way how we did in the probability, first part of the probability unit. We know we're going to have 5 messages. And we want that 5th one to be the real message. So that's going to be our 0.09. All these others are going to be 0.91. Or we're saying 0.91 to the 4th power times 0.09. Okay? And we do like to usually associate the probability that x equals 5 because it is a random variable. And we just type that into our calculator, and we do get about 0.062. All that's left for us to do is our statement in context. So here's our answer. There is a 6.2% chance the first real message will be the 5th email checked. And that's it. Let's look at another. This time we have people with O negative blood type are called universal donors because O negative can be given to anyone else regardless of the recipient's blood. Only about 6% of people have O negative blood. If donors line up at random for a blood tribe, how many do you expect to examine before you find someone who was O negative blood type? Okay, so let's do our check, right? Do we have 2 outcomes for binary? Yes, they're either O negative or they aren't. Do we have the probability of success is constant? In this case, we do yes, because if we're talking about all people, odds are our sample is going to be less than 10% of our population. Okay, and is our probability of success constant? Yes, and we have independence because of the 10% rule. So now we are ready to do expected value. We know for certain this is a geometric probability. So here is our expected value. Remember, it's 1 over the probability of success. So remember to change the 6% to a decimal and then type it into a calculator. It does end up being about 16.67 people. And then all that's left for us to do is our statement in context. Okay, so here's our statement in context. For blood drives such as these, we can expect to see an average of 16.667 donors until a universal donor is found. If we look at the next bullet, we have what is the probability that the first O negative blood donor is the 6th person in line. Okay, so this is the same thing as we did with the email example. I mean, we could draw 6 blanks, and I want the 6th one to be the first O negative blood type. So we're going to have the probability of X equals 6 equals. Now, remember we want that 6th one to be the first. So that means the 5 before that 6 in line are some other blood type. So we'll do the probability of failure, which in this case is 0.94 to the 5th power. Okay, and this does end up being about 0.044. And then all that's left for us to do is to write our statement in context. So in context, we have about 4.4% of the time the first O negative donor will be the 6th person. Let's look at part C. Okay, so this time, what is the probability that the first O negative donor is one of the first 4 people in line? Okay, so if I want to find the probability of one of the first 4, that means we're doing the probability of X is less than or equal to 4, because I don't care if it's the first, the second, the third, or the 4th. So what we can do is the first one, we definitely want to be the O negative. So that would just be 0.06 plus. We can do the 0.94 as the first failure and the second person being the first O negative. Then we can do the third. Right, so that means the first 2 are 0.94 because there's some other blood type, and the third is 0.06 plus 0.94 to the third times 0.06. And then you would type that long expression into a calculator, and this is 0.219. Now, the other thing you can do, as long as you label, you can use there's a command called geometric CDF, and you get there by pushing second bars and scrolling down on the calculator until you find geometric CDF. And then you put your probability of success in, and then our number 4. So you believe you have to label your P and your N, and you also have to highlight, right? You have to have the inequality statement with labels on your geometric CDF command. And you do get the same answer, 0.219. Okay? And then all that's left for you to do is your statement in context. So here's our statement. On average, about 21.19% of the time, a universal donor will be found by the 4th person in line. So now let's say we have, suppose you buy 5 boxes of cereal. What is the probability that you get exactly 2 pictures of Tiger Woods? Okay, so remember, we're thinking in our brain. We talked about this early. We're talking about bins. Okay, do we have 2 outcomes? Yes, we do, because it's either Tiger Woods or it's not. Do we have independence? Well, if we're only buying 5 boxes of cereal, is that less than 10% of the population of that type of cereal box? Yes. Do we have a fixed number of trials? Yes, we have 5. And then is our probability of success, meaning we want Tiger Woods, constant? Yes, it is 0.2. So this is actually a binomial model because it's a probability describing the number of successes in a specified number of trials. Okay, so that is the difference. And if you were in pre-calc last year, this formula should look familiar because this is the binomial theorem. Okay, notice we have our mean, n times p, and our standard deviation, the square root of npq. And I believe all those are on the formula chart. So remember our bins. B is for binary, 2 outcomes. I is for independent trials. N is the number of trials that are fixed. And S is the same probability of success. Okay, so now let's go to an example. A new drug that is 75% effective is given to 20 patients. What is the probability that exactly 15 people will benefit from this drug? Okay, so first check. Do we have 2 outcomes? Yes. The drug is either effective or guess what? It's not. We have independence, right? Is it safe to assume patients are independent of one another? In this case, yes. And what is the probability of success? Well, it's 0.75. And is it constant? We're assuming for the population. Yes. And do we have the number of fixed trials? Yes, we have 20. So we are good to run with our binomial model. Now, because this is still a random variable, you still have to write that p of x statement, and it's going to equal 15. Now, we know we have 20, and we're choosing 15. Now, remember, if I have something like n above r, this is how I do it algebraically. Okay, but remember the calculator will do it for us. So 20 choose 15. We know 0.75, we want exactly 15 to be effective. And so that means 5 or not, and the probability of failure is 0.25. And you would type that into a calculator. Now, in order to do the combinations, this guy, you would type 20 first, then you would push math, and you would go to probability, and then select either option 2 or option 3, NCR. And then after you would see 20, and then I believe it says NCR, you would type 15, and then you can type the rest of the expression as normal. Okay, so this does give you 0.202, or about 20.2%. The other thing you can do is you can use calculator speak, although I will warn you, you need to be familiar with the formulas because they like to appear on multiple choice questions with just how you would set up the formula. Okay, if it's asking for a binomial probability, there is a command called binomial PDF. And you would do 20, comma 0.75, and then comma 15. However, if you're going to use binomial PDF, you do have to label your N and your P for sure. And this also gives you the 0.202. Now, if you need to know where to find binomial PDF, you would push that second vars and you would scroll down until you find binom PDF. But you have to label everything. If you just write binom PDF in the 3 numbers, you will not get an essentially correct. Let's go back to that email spam problem from Postoni. And this time we're going to say, suppose our inbox contains 25 messages. What are the mean and standard deviation for the number of real messages you should expect to find in your inbox? Okay, so we have to ask ourselves, are we going to use this geometric model or is this a binomial model? Well, remember, we said 91%. That was our spam probability. Okay, and notice we have a fixed number of trials. We have 25. So this one is binomial for that reason. Okay, so remember to find the mean of a binomial model. We have E of x equals mu, which is 25 for our messages. And are we going to use 91% or are we going to use 9%? Well, notice it says the number of real messages, so we're going to use the 9%. And then we just type that into a calculator, and it is 2.25 messages. Okay, and then to find the standard deviation of x equals sigma, which equals the square root of NPQ. So 25 times 0.09 times 0.91. And this does give you a decimal of approximately 1.431. And that's it. So if we look at the next problem, it says, what is the probability you'll either find one or two messages? Okay, so that would be probability of x equals 1. If I see 1 or 2, that means you're going to add your probabilities. I'm going to change my color. Okay, so the probability of 1, you would take 25, choose 1. I want that first one, I need one of them to be real, and the other 24 to be spam. And I'm going to add that the probability of 2 real messages. And then just type all that into your calculator. This does give you an approximate probability of 51.2%. Oh. Okay. Now, that's a decimal. What you could have done instead is you could have done a binomial, or I think I forgot my statement. P of x, plus P of x equals 2. Okay, so you would have your binomial PDF. You would have your 25, success, and then 1, plus binomial PDF. And then you have to label N and P. Okay, and this does give you a probability of about 0.512. Okay, and either way would be deemed acceptable. As long as if you're using binomial PDF statements, you have the labels. Okay, so now we're going back to that blood drive example. So notice we have 20 donors, and remember that 6% are the universal donor. So notice we have mean and standard deviation of the number of universal donors among them. So we're going to ask ourselves again, is this binomial? Is it geometric? Which one is it? Well, because we have this fixed number of donors, like we know we have 20 altogether for certain, it is a binomial model. Okay, so all that's left for us to do is to find the mean and standard deviation. So because it is binomial, we're going to do our E of x equals mu. And remember, you're going to take your n, which in this case is 20, times the probability 0.06. Okay, and this does end up being 1.2 donors. Okay, and then for your standard deviation, you're going to take the square root of NPQ. So 20 times 0.06 times 0.94. Okay, and this does end up giving you about 1.063 donors. And that's it. Now if we look at the next question, it says, what is the probability there are no more than 3 universal donors? Okay, there's a couple different ways that you can do this, you could list the probability of no more than 3. Probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3, but it's binomial. If I had it my way, I would do the probability that x is less than or equal to 3. And there's a binomial feature in the calculator called binomial CDF, which stands for cumulative probability. And you would do your 20, comma 0.06, comma 3, and you would label the n and the p. Now, I've already made the, nope, no I haven't, never mind. Remember, you have to have your statement here and you have to have your labels. Otherwise, they will ding you on the AP exam. So when you type this into a calculator, you would push second bars and scroll down the binomial CDF. It does end up being 0.971. Okay, so let's just, for funsies, say we wanted to find the probability that there are at least 5 universal donors. So remember, at least means 5 or more. So I would have to find the probability of 5 plus the probability of 6 plus 7 plus 8 plus 9 all the way to 20, which can be very tedious. Well, what we can do instead, we know the probability of x is greater than or equal to 5 is the same thing as 1 minus the probability of x is less than or equal to 4, right? So what we're going to do is we're going to do 1 minus 4 or fewer. Now, binomial CDF in the graphing calculator only works for less than or equal to probabilities. So we would set up binom CDF, and we would do our number of people, 20, that's our n, our probability of success, 0.06, and then our number of people in our statement, 4. And this does end up giving us about 0.006. Okay, so notice that we have our statement and we have our labels. Okay? This time we know that 38% of all people have O positive blood type. What is the probability that the next 8 donors who randomly come in the donation center that at least 5 have O positive blood? Okay, so remember, we want to find the probability of at least 5. So x is greater than or equal to 5. That means I want to find the probability of 5 plus the probability of 6 plus the probability of 7 or plus the probability of 8. Okay, so this could be a very lengthy probability statement. I mean, you would have to do 8 choose 5 0.38 to the 5th, and then 3 left over. What's the 5? 0.52? No. 62 to the 3rd plus 8 choose 6 0.38 to the 6th times 0.62 squared plus 8 choose 7 0.38 to the 7th times 0.62, and etc. Or what you could do is you could do 1 minus the probability of x is less than or equal to 4, and that would be 4 or fewer, and we can use that 1 minus that binom CDF. And we have our 8, we have our 0.38, and we have our 4, and we label our n and our p, and it will give you the same answer of 0.1443. And that's it. You're ready for practice. The end.